In this last lecture on rectangular waveguides, I'm just going to talk about a couple of the important practical concepts. There's not going to be any tutorial questions associated with this, but some of the information that you see from here will talk to you a little bit about how you choose waveguides for different problems, and we'll talk a little bit about loss. The objectives for this are pretty straightforward, and they're really just knowledge-based objectives. So we want to understand what the loss mechanisms are in metallic waveguides, so you should understand what those dominant sources are. You should be able to use data sheets in order to be able to understand the loss characteristics for any particular waveguide. And then we also want to understand the waveguide standards and how you pick waveguides for various applications. And so you should be aware of these and be able to read the data sheets to choose the proper waveguides for an application. So just to re-emphasize again, talking about the mode visualization, we're looking at here at some of the lower order modes in the TE and the TM case. This is a plot from Posar's textbook, and we're looking at the field lines. We're pretty comfortable with the TE10 mode distribution. So here we're looking at the cross-section of the rectangular waveguide, and we see the electric field is oriented vertically, the magnetic field is oriented horizontally, and we know it varies like a cosine as we move across the guide. So I have cosinusoidal behavior because that y component of the field must go to 0 at the edges. What we're looking at here is down the path. So as I go down this line, that's going in this direction on the in the central axis of the waveguide. So we see the fields point up here, and then down here, and then up here, and then that's the guide wavelength. And this is looking from above. Looking from above, we see that the magnetic fields are actually circulating. So the electric fields are pointing up and down, and those are indicated here by these dots. And the electric fields are pointing up and down, but the magnetic fields are circulating in the XZ plane. And that's what gives rise to the propagating modes. As this magnetic field circulates, it needs to be supported by a time-varying electric field, or displacement current density. So at this instant in time, I've got this circulating magnetic field. Right? That circulating magnetic field will cause an electric field to grow. And as that electric field grows, the energy from the magnetic field will move into the electric field. Likewise, this electric field will give rise to a local magnetic field, and so the energy will slosh back and forth between the electric and the magnetic cases as it goes down the line. Go up to the next higher mode, the TE11 mode. In the TE11 mode, we see that we have these electric field lines that are perpendicular to the surface, because we know that at the surface of a perfect conductor, the electric field lines must be 100% perpendicular, and that's borne out in this picture, coming in completely normally. But the magnetic field lines are circulating a little bit, and again in the side planes, we see what happens looking from the side and from the top. And as we go higher in mode index, things get a little more complicated. The TM11 mode is a mode that looks a little bit like a coaxial mode. We see that the electric fields are pointed out for the most part. There's a little bit of bend that forces them to come normal into the surface, and the magnetic fields are circulating around those lines. So as Greg mentioned in class on Thursday, there are some waveguide standards. These are the waveguide standards and the associated bands of operation. The EIA designation, the WR-XX, which is shown here in this column, that is giving the waveguide size, and the number stands for the dimensions of the waveguide in in hundredths of an inch. And so WR90, which is here, has a waveguide size which is 0.90, so 90/100ths of an inch wide. Right? Now, we looked at this in class on Thursday. We see that the WR90 has a cutoff frequency for the TE10 mode of 6.57 gigahertz, but the recommended range of operation is a little bit removed from that. It's 8.2 to 12.4 microns in and around the X band. As Greg indicated, we have different bands. L band is around 1 gigahertz. We see that the waveguide is 6.5 inches in size. As we go higher in frequency, the waveguide will get smaller and smaller and smaller. We'll talk a little bit about loss mechanisms. In coaxial cables, we know that there are losses in the conductors that carry the current and the dielectric that insulates the line. We've seen several tutorial problems looking at the losses in coaxial cable. We know that the conductor losses dominate, and those are dominated by the inner conductor. The inner conductor is very small. It's got a very tight radius of curvature that gives rise to large electric fields near the conductor. And then at higher frequencies, you have very narrow skin depths, and that can lead to large loss. And so this is a list of some of the more common coaxial cables taken from Posar's textbook. And as you can see, there's fairly significant attenuation. If I look at 1 gigahertz, all of these cables have loss of 10 dB per 100 feet or more. And so there's a significant amount of loss going on in these sorts of cables. In rectangular waveguide, I don't have that central conductor, which has the large fields and therefore carrying a high current density. The currents instead are carried on the exterior walls. And the walls are flat. Right? So there's no field enhancement due to the small radius of curvature. I can compute the current on the side walls by using the boundary condition. This is always the case. I take the normal vector, so say I've got a vertical wall here. I take the normal vector and I cross into the H field, and that's going to give me a surface current flowing on that wall. And I can compute, or I can treat that surface current as, say, a uniform current density flowing within a finite width region that's given by the skin depth. Way back in lecture 2, we did a tutorial problem where we looked at current that was decaying exponentially inside a conductor or inside a material. And we looked at the problem of how do I take that decaying current and relate it to a surface current. And that's exactly what we're looking at here. So, except we're going in the other direction. We can compute a surface current for perfect electrical conductors by taking N cross H. But we know that it's not a perfect conductor. We know that the current is actually going to be flowing for some finite distance inside the guide, inside the metal of the guide. And this is a plot from microwaves101.com. It's an organization that publishes some tutorials on microwave parameters. They're not all complete, and in fact the one on loss isn't complete. It's published in association with the IEEE Microwave Theories and Techniques Society. But what this is plotting here is it's plotting the loss in dB per meter of some of the standard waveguides. And so WR90 is here in blue, right? And we see that we have losses in WR90. I got the wrong one for WR90. WR90 is down here, right? And so the loss in the X band is going to be a fraction of a dB per meter. And so we can see that the losses are significantly lower in waveguide than they are in coax, as we saw in the previous, because in the coax. So at lower frequencies, we know we can deal with the losses associated with the conductors, and we can use coaxial cables. When we start getting up into the gigahertz type frequency range, there's a trade-off between the advantages provided by a coaxial cable and the disadvantages provided by its loss. And so in the gigahertz sort of range, we'll often use either coax or waveguide, and that really depends on the power levels. When we have fairly high power levels, it's generally preferable to use waveguide, whereas at lower powers we can get away with using coax, and that's because at higher powers, if I have more loss, I have more heat dissipation, and that heat dissipation will cause me other problems beyond electromagnetic problems. But as I go further and further up in frequency, and as I start to approach the sub-terahertz, so several hundred gigahertz into the terahertz sort of regime, the conductor losses can grow quite large, and dielectric waveguides become attractive. Dielectric waveguides will be the subject of the next lecture, and dielectric waveguides use optical methods, and without the conductor, the resistive losses can be ignored, and the only losses are associated with losses in the dielectric medium itself. However, as we'll see in the next lecture, they come at the expense of having a non-confined mode. So if I have a high dielectric constant core with a low dielectric constant cladding, and that's how I make a dielectric slab, I don't have my fields confined just to the core. I have some leakage of the fields into the outside world, and that can create some challenges. So there's no specific tutorial topics associated with this lecture. However, the practical details here are the ones that could come of use to you. If you know you have to work in a particular frequency range, you can go to your textbook POSAR and look up what waveguide you want to be getting. There are many different manufacturers that will make waveguide to those specifications. You can find those waveguides and look at their properties, and depending on what material they're made out of, you can look at their loss and be able to decide what's going to work for your particular application.